Hello and a very warm welcome to MSc Online Classes. We are into the seventh session of Network Analysis and Synthesis. Today we will be dealing with loop and nodal analysis and graph theory. In the previous session, we have already discussed various interrelationships between different matrices in graph theory. Today I'll be using those relations to do loop analysis and nodal analysis in graph theory. Now, let me consider one primitive branch element. Here in this branch, I have considered all the possible elements that we could have connected. For an example, we have connected an impedance here. If there is a voltage source connected in that very branch, then we have connected a source of Vs volts and we have connected current source in this branch again. Okay. So this is maximum possible components which a branch can have. It may or may not consist of all these elements. It may consist of Z alone, Vs alone, or Is in parallel with Z. So this is what we have in the first session of graph theory. I have told you how to draw graph. So for any branch, you can have these two in series, or you could have a single Z element, or you could have a parallel combination of Z and Is. So let's just start. Let's say I have assumed that we have a branch connected between node A and B in the network. I have assumed IB to be the branch current. Let the source current is having a value Is and the voltage source is of magnitude Vs. Let the impedance connected in the branch is Z. Now we can write KVL in this. Applying KVL, if I say VB is the branch voltage, and I have assumed the polarity, this end is positive with respect to this end, therefore I have assumed current to be flowing in this direction. Now I can write KVL in this loop. If I apply KVL in this, then I can write it as VB is equals to, now VB here is branch voltage, that is the potential across A, B. So VB is equals to क्या हो जाएगा? Now see, Vs plus Z into, if I say this to be ZB, so it is ZB into IB minus Is. Since current flowing through this ZB element is the difference of these two current, since I have assumed Is to be having this direction, Is is direction mein hai, IB is assumed in this direction, therefore the current, as per KCL, the current flowing in this branch is IB minus of Is. So drop in this impedance is given by Ohm's law, and it is ZB into current flowing through that impedance element. So this is drop across this ZB plus Vs, and this is the total potential across the branch. Now let me multiply both sides with BF. So multiplying both sides with BF, I'll get BF into VB is equals to BF into Vs plus BF into ZB IB minus Is. Here IB is branch current, ZB is the impedance of the branch, Is is the value of current source connected across that branch, and similarly VB is the branch voltage and Vs is the source voltage. I hope it is clear. And we already know that BF into VB, earlier we have drawn that BF into VB is equals to 0. So I can put this value equals to 0. So now my equation becomes 0 is equals to BF into VS plus BF into ZB. Now we have also derived a relation between branch current and link current vector, and that says, I'm writing it here, IB is equals to BF transpose into IL. ये ऑलरेडी ड्राइव कर रखा है हमने. अगर किसी को ये इसके बारे में देखना है तो वो प्रीवियस सेशन 6 सेशन को देख सकता है. तो बी एफ इंटू जेड बी यहाँ पे था. आई बी की जगह आई एम प्लेसिंग राइटिंग बी एफ ट्रांसपोज इंटू आई एल माइनस आई एस. आई होप इतना समझ आ गया होगा. नाउ इट इज इक्वल टू बी एफ इंटू वी एस प्लस बी एफ जेड बी इंटू बी एफ ट्रांसपोज आई एल minus BF ZB IS. Now let me take these two terms on the left hand side. I'll get BF ZB into IS minus BF into VS equals to BF ZB BF transpose into IL. Now see, this is your link current vector, या जितने भी लूप करंट वेक्टर कह सकते हैं. फॉर एवरी लिंक कनेक्टेड टू योर ग्राफ यू फॉर्म अ फंडामेंटल लूप. और फंडामेंटल लूप क्या होता है, इसके लिए प्रीवियस जो हमारे सेशंस हैं उनमें आप देख सकते हो. वहां पे मैंने डिफाइन किया हुआ है कि व्हाट इज योर फंडामेंटल लूप. तो ये जो लूप करंट वेक्टर है ये क्या ले रहा है, इफ यू आर हैविंग 2 or 3 f loops, then it is a column vector with IL1, IL2 and so on loop currents. Now it is multiplied with this. Now let me say that this is your loop impedance matrix, and loop impedance matrix is nothing but it is BF ZB into BF transpose. Now relating, if we multiply these two, Z into I, it gives you V as per Ohm's law. So I'm saying that this entire term is loop voltage vector. And अगर units भी देखें तो ZB into IS will give you a voltage term, and here again this is a voltage term. BF matrix, this is having only 0 or 1 value. ठीक है, तो ये तो आपका रियल नंबर है, तो ये यूनिट्स पे तो कोई इफेक्ट नहीं डालेंगे. ZB into IS, again the multiplication of these two terms will definitely be giving you voltage terms, and again VS matrix, it would also have only voltage values. Therefore we can say VL to be equals to BF into ZB into IS minus BF into VS. Now if I am representing your equations, various equations, this is for one branch. Similarly you will be having many branches. If you are having B number of branches, then B such equations would be there. ठीक है, B such equations, it means इस तरीके की आपकी उतनी इक्वेशंस होंगी जितने आपकी ब्रांचेस होंगी. ठीक है, तो इस तरीके की जितनी इक्वेशंस होंगी, अगर उनको आप इस फॉर्म में लिखें तो इसको हम कहते हैं मैट्रिक्स लूप इक्वेशंस. तो here from this we can determine the value of loop current by taking the inverse of ZL matrix. That is, if we have the value of VL and ZL, then we can determine IL to be equals to ZL inverse into VL. VL and ZL can be determined using these relations. You can determine the value of VL to be equals to BF. कोई भी ग्राफ होगा, you can develop BF matrix And if you don't know how to develop BF matrix, you can see my previous sessions of networks. There I have taught you how to develop BF matrix. Now this ZB is your branch impedance matrix. It is a diagonal matrix with B cross B order, and every diagonal element is the impedance of every branch. For an example, you have 5 branch, so it would be a 5 cross 5 branch with diagonal elements equals to Z1, Z2 and up to Z5, provided there is no mutual coupling between various branches. If there is any mutual coupling between any two branches in the network, then it is not a diagonal matrix. Non-diagonal elements may also be having a non-zero element, but only in case of your mutually coupled branches. Clear? Otherwise, it is going to be a diagonal matrix. Now, IS here is your source current vector. You can write this source current vector seeing the network. So, if you have any current source associated with any particular branch, then you will mark that element to be having that value of current source. Else, you will be marking 0 for remaining branches if there is no current source associated with the branch. Similarly, if you have a voltage source connected in any branch, then you will be marking the voltage element. You will be marking that element equals to the value of the magnitude of that voltage source. Else you will be marking 0. तो आगे मैं आपको बता रहा हूँ कि किस तरीके से आपको VS और IS लिखना है. तो to obtain VL, we have all the values of ZB, IS and VS. We can get it from just seeing the network topology only. Now similarly, we can also develop a ZL matrix merely multiplying these three matrices. I hope I'm clear here. So we can get VL and ZL, and now for IL, what we can do is, I have already told you, we can take the inverse of Z matrix, ZL matrix, and can multiply it with VL. So there we can get IL matrix. Now also we know that, IB is equals to BF transpose into IL. Now if we have obtained loop current vector, then definitely we can, with the help of this relation, we can determine branch current vector, and this vector would consist of all the branch currents. If you are having B number of branches, so it would be a B cross 1 matrix having all the elements to be equals to the branch currents. So if in the question it is asked from you to determine branch current through any particular branch element, then definitely you can use this method. And if you are using this method, this is known as loop analysis. I hope ये समझ आ गया होगा, बहुत इजी है. ठीक है. Next is nodal analysis. In nodal analysis, what we are going to do is, we shall consider that same network which we have already considered for loop analysis. See this network. Here, if I want to write the value of IB in terms of other admittance form, if I want to write current, I as a function of V and Y, so I can write it as IB is equals to, writing KCL, IB is equals to IS plus current flowing in this branch. So IB is equals to IS plus current flowing in this branch, and in terms of voltage vector, I can write it as YB if the branch admittance is YB into VB minus VS. VB is the potential across these 2 points, minus of VS, this is the potential across this ZB element. So potential across the ZB element is VB minus VS, multiplying it with the admittance of that branch, I'll get the current flowing through that branch element. So this is the equation which we are going to use in nodal analysis. So remember this. Now let me write it here. IB is equals to IS plus YB into VB minus VS. Now we can use these matrix, this equation in 2 ways. I can multiply this matrix or this equation with A matrix, and we also know that KCL in graph theory is A into IB is equals to 0 and QF into IB is equals to 0. Now if I multiply this entire equation with A, then it is A into IB is equals to A into IS plus AYB. And do we have any relationship between VB and VN? Yes, we have. VB is equals to क्या होता है? A transpose VN minus VS. ठीक है? Now A into IB we already know it is equals to 0. So it is equals to A into IS plus AYB, A transpose into VN minus AYB into VS. I hope it is clear to you. Now let me take these 2 terms on the left hand side. I'll get AYB VS minus A into IS equals to AYB A transpose into Vn. Now this is your node voltage vector, and in nodal analysis, previously in basic electrical engineering, we also know that while solving a network using nodal analysis, what we do is we assume node voltage variables with respect to a reference node, and then after determining the values of Vn, then we can determine the current flowing in any branch of the network. Now we are using the similar approach here, therefore this approach is known as nodal analysis. Now let me name this matrix as Yn. Now this is node admittance matrix. Vn is equals to AYB into VS minus A into IS. Now node admittance multiplied with node voltage variable would definitely be giving you node current vector. So this equation is known as matrix node equation. I hope it is clear to all. If you have any query regarding loop or nodal analysis, do write in the comment section. I'll be answering there. Okay. Now this is one method. If we would have multiplied this equation with QF, then certainly I would have got QF into VB, and either on the right hand side again I can multiply this equation with QF. Now again QF into IB is 0. So similarly we can obtain one more relation. So for nodal analysis, let me write one more relation in terms of cut-set matrix. So IB is equals to IS plus YB into VB minus VS. Multiplying both sides with QF matrix, so it is QF into IB equals to QF into IS plus YB. Now, do we know any relation between branch voltage vector and cut-set matrix? Yes, we have a relation. We have VB is equals to QF transpose into VT. And for this relation, please watch my previous lecture on network analysis. There I have derived a relationship between VB and VT minus Vs. Now, as we know, QF into IB is 0. So therefore, on the right hand side, it is QF into IS minus YB QF transpose into VT minus, sorry, there's one QF here also, okay, minus QF YB into Vs. Now take these two terms on the left hand side, we'll get QF YB, it is YB into Vs minus QF into Is equals to QF YB into QF transpose into VT. So similarly, I can say it to be YT VT and this as IT. I hope it is clear to all. And this equation is known as node pair equation. And this is your node pair admittance matrix. I hope it is clear to all. If you find any doubt, then do write in the comment section. I'll answer that. And in the next session, I'll be taking a few examples wherein I'll be using loop nodal analysis to solve for the branch current. And we are left with one more topic, that is duality. So in the next session, I'll be covering that topic also. I'll be covering duality in the network and we'll consider one example. And it is only important in case of university exam. You will not find any question from these topics in the competitive exams. So I hope it is clear to all. Thank you for joining, and you may see a subscribe button here. So do like and comment and hit this button to subscribe for the MSD online classes. Thank you for watching.